Hello and welcome to Chapter 2, Graphical Descriptions of Data. We're going to be using R for the assessment portion of Chapter 2, and that'll also make sure that we've covered the use of technology. Section 1 is about categorical data, so we're going to look at frequency tables, bar charts, pie charts, Pareto charts, and multiple bar charts. First thing we're going to look at is a frequency table. So here is an example of a frequency table and a relative frequency table. So because these are categories, they've got different rows. We might put one count in each column. And sometimes if you look at that rightmost column, we can take the frequency and divide it by the total to get the relative frequency. It's the same as the percentage, but written as a decimal. The next thing that we're going to look at is bar graphs or charts. So again, for categorical data, we're going to put the categories on the horizontal axis and the frequency on the vertical axis. So that's the same information from the previous page, just made into a bar chart. So what are the key features of a bar chart? There is an equal spacing on each axis. The bars are all the same width, and there should be labels on each axis, so we know the frequency and the car type, and a title for the graph. There should be scaling on the frequency axis, and the categories should be listed on the category axis. That scaling is the numbers along the vertical axis. The bars do not touch, and we should start at 0 unless we've got a good reason not to. So relative frequency bar charts, we can also draw these with the relative frequency on the vertical axis. This is useful when you want to compare two samples with different sample sizes. The relative frequency graph and the frequency graph should look the same, except for the scaling on the frequency axis. A pie chart is exactly what you'd expect. You've got that circle divided into sectors, and those sectors represent the frequency or the percentage of each. So that's the same data being represented again. It's important to be wary of colors. This looks really good in color, but on my black and white printer it doesn't look quite so good. It's really hard to tell Chevy from Toyota, for example, even though it is easy to see it in color. And perhaps more importantly, avoid color legends, in other words, saying what a color is meant to represent, because it's usually very hard to match up what that actually is representing. A Pareto chart is the third type of way we're going to display categorical data. It's a bar chart. It's exactly the data that we had before, but it is sorted so that the highest frequencies start on the left. So Chevy and then Toyota, they're in alphabetical order because they have the same frequency, and then decreasing as you go to the right. So a bar chart that has been sorted so that it starts with the most frequent items. A multiple bar chart is useful when there's several things going on. It's easy to do in many computer applications like Excel or LibreOffice. You kind of have to use colors when you've got this, so make sure that the use that this graph will be put to is appropriate for that whoever is looking at it is able to sort those out. Quantitative data can be shown through a frequency distribution table, a histogram, an ogive, or a stem and leaf plot. A stem and leaf plot could be thought of as a histogram for typewriters. So we're going to talk about making histograms. There's a lot of steps here, and on the next page we're just going to talk through them. R will take care of all of this for us. But it's good to know what it's doing. So we're going to go quickly through this. Feel free to stop and go back if you need to, but here we go. So we start by making a frequency distribution. So we divide up the range of data into frequency classes or bins. We count how many observations fall into each bin. And then we make the histogram, which is a bar chart of those frequencies. One difference from regular bar charts is that the bars touch one another. And that's because we've got quantities that we're dealing with now. So the steps in more detail. So we need to find the range, and the range is exactly what it was in an algebra class. It's the largest minus the smallest. We pick the number of classes to use, and you'll see in the project that you do in place of an exam for Chapter 2, the number of classes affects the look of the graph tremendously. So this is something you can experiment with, especially with technology. 5 classes are used if there's a small number of data points, and 20 classes if there's a large number of data points. That's over 1,000. And we're going to call those categories classes from now on. The class width is the range divided by the number of classes. Always round up to the next integer if you've got a decimal. And even if the answer is already a whole number, round up to the next integer. If you don't do this, your last class will not contain your largest data value, and you'd have to add another class just for it. If you round up, then your largest data value will fall in the last class and there are no issues. So always round up, even if you've got an integer. Create the classes. Each class has limits that determine which values fall in each class. To find the class limit, set the smallest value as the lower class limit for the first class. Then add the class width to the lower class limit to get the next lower class limit. Repeat until you get all the classes. The upper class limit for the class is 1 less than the lower limit to the next class. We're going to order the classes to actually touch. Then one class needs to start where the previous one ends. This is known as the class boundary. To find the class boundary, subtract 1/2 from the lower class limits and add 1/2 to the upper class limits. You can do this by finding midpoints. The midpoint is just the sum of the lower and the upper divided by 2. That's the class midpoint. To figure out the number of data points that fall in each class, go through the data values and see which class boundaries it is between. And usually this is done with tally marks, just as a convenient way of counting those up. The frequency for a class is the number of data values that fall in the class. The previous distribution is for counting numbers. For continuous numbers, we need to use half-open intervals to create our bins. So let's look at an example like that. So here are some half-open intervals for letter grade assignments. We don't use partial grading where there's A's and B's. One of the weirdest things about partial grading, if you've ever been to a school that uses it, is that there's next to never an A+. So when you look at that and you think, well, where on earth is the A+? There isn't one. So it's kind of hard to understand the value of these partial grading systems. Notice that an A contains everything in the interval from 94 to 100%. An A- includes everything from 88, including 88, that's what the bracket means, up to 94. The parenthesis at 94 means that it ends at 94. In other words, 94 is an A, and instead of having 2 values for a 94, that parenthesis says that everything up to 94 from 88 is included, but a 94 itself is not included. That's why these are half open. A bracket on one side to say that that value is included, a parenthesis on the other side to say that that value is not included. So let's look at some rental data. So here's the data itself. So the first thing that we're going to do is find the range. So we need to find the max and the min. We take their difference. We see that the range is $2,200. We choose a number of classes. In this example, 7 was chosen. We then figure out the class width. So we take the range and divide it by the number of classes. We get 314.286. We round that up, and we'd round it up even if it was a whole number, but certainly in this case to 315. We then compute the class limits. So we start at the minimum, 350, and we go 315 more. And then we add and subtract 1/2 to get the class boundaries. The class midpoint is just their average. That is their sum divided by 2. Notice that those dashes in the class limits and class boundaries are just saying a range. So that's non-standard math notation, but you'll see it in statistics a lot. That's not a subtraction symbol, in other words. The tally is as we go through the data and we count how many data points are in that class, and then we write that number as a frequency. So notice that there's two classes that have a frequency of 0. So here is the histogram. So the monthly rent is the label at the bottom. Notice that to keep there from being too many numbers bashing around, each class is shown with its midpoint. So that 507 is the midpoint of that first class, and the frequency is 4 for it. There are 2 zeros there with those two classes up there towards the higher end, and then a frequency of 1 out at 2,397. So we now talk about outliers. And outliers are an issue that we can best see, but they're an issue throughout the course. In fact, one of the last things that we'll do in the course is deal with outliers in situations where they'd cause us grief otherwise. So in a very general term, an outlier is a data value that is very far, or simply far from the rest of the values. It may be an unusual value, like that one rent that was significantly higher than the others, or it may simply be a mistake. It is a value that should be investigated, in other words. If it's unusual, there's probably a reason for it being unusual. If it's a mistake, then it's probably best to throw it out. In classical statistics, there is a great fear of outliers. They have an ability to change our results. In more modern Bayesian statistics, outliers are often seen as a trajectory into the future. In this case of rent, I think we've all seen that. It's a data value that should be investigated. We need to figure out what's going on. In this case, the student lives in a very expensive part of town, thus the value is not a mistake, it's just very unusual. There are other aspects that can be discussed, but first some other concepts need to be introduced. So a relative frequency histogram just takes those tallies and divides by the total. So this looks like exactly the same histogram we saw earlier. The only thing different is the vertical axis. Now instead of being the frequency, it's the relative frequency. That is the percentage as a decimal. So a cumulative frequency distribution basically includes everything below that value. To create a cumulative frequency distribution, we count the number of data points that are below the upper class boundary. And not just in that class, all the data points below that upper class boundary, starting with the first class and working up to the top class. The upper class boundary should have all the data points listed in it. So once you get to that very last upper class boundary, you've got everything. So that last point should actually be the total. Also include the number of data points below the lowest class boundary, which is 0. So we've got a true 0 here. So an ogive is a plot of a cumulative frequency distribution. So here is a plot of a cumulative distribution, which is called an ogive. So we start with our 0. There's no rent that's 0, so we see that first point a little before 500, and increasing as we go to the right. Now, this is one of those things that's always a little bit weird for me to understand. It probably shouldn't be, but it definitely is. Certainly the first two make sense. When you look at a roughly symmetric graph, you think, yep, it looks like it goes up and then it goes down. It's symmetric to the left and the right. If you folded it along the tallest bar graph, you would see pretty much the same thing on the right and the left. The second example, a bimodal but symmetric graph, has two peaks, but it's symmetric to the right of those two peaks. In fact, it's symmetric perfectly to the valley in the middle. And when I say perfectly, it's not perfectly symmetric. This is the general flow of the data. Now, skewed right, the way I think of this, and the way that allows me to remember this, because this data does not look skewed right to me. This data looks as if there's more data to the left. So the skew is the tail. It's where the data tails off. It's almost like someone pulled the data to the right, right? It wanted to be kind of clumped to the left, but someone pulled it to the right, which is my kind of silly way of thinking about how you'd make this data. It tails off to the right, therefore it's skewed to the right. Similarly, skewed to the left means that it looks like someone kind of pulled the data off to the left side. It's mainly highest out to the right, but the tail diminishes off to the left. And of course, a uniform graph. Everything has the same frequency. It's all the same height. So now let's talk about other graphical representations of data, including the stem and leaf plot. So a stem and leaf plot basically makes a histogram using a typewriter. In other words, you just stack up the numbers. You can make this with a word processor. You don't need something sophisticated. We're going to then talk about scatter plots and time plots. Time plots are ubiquitous. We're always going to put time on the x or the horizontal axis, and that'll allow us to show what's happening over time. That trend may be growth, or it may be a period of growth followed by a period of decay, growth and decay, like the length of days in the year. Days get longer as the winter passes to summer, and then shorter again. So we're going to start with some data for a stem and leaf plot. We first need to figure out the range of this data. It looks like it ranges from the 40s to the 90s. So then we're going to pick off a particular data point. So that first data point is 62. So we see that in the 60s, we're going to put a 2. Basically, that counts, that digit 2 is like a tally. It's saying that there is one number in the 60s. And then we continue in this way. So for example, when we look at that 87, we're going to find where it is, and we're going to put a 7 in the 8 row. So there's the 87. The only thing that we needed to add was the 7. Basically, that's adding a tally of 1 in the 8 column. And if you take this and you put it on its side, or just cut it and rotate it, which is what people used to do, you get a box and leaf plot. So that's this here. So just rotate it. So hopefully you can see the 62. It's a little sideways, but you can see it. And you can see the 87. And then all the other numbers as well in their respective classes of width 10. So this makes a histogram without a lot of work, and certainly before technology came along, that was really, really important. We're now going to talk about a scatter plot. So we're going to talk about something kind of related to adiabatic cooling. It looks like as we go up in elevation, the temperature falls. So let's take this data, and of course I can say that because I'm looking at the scatter plot. It's much harder to see looking at the data itself. That table with the elevations in the top row and the temperatures in the bottom row looks like just some kind of fairly random collection of data. I don't see a trend until I put it in the scatter plot. Now, you might say that trend is fairly weak, and I definitely agree with you. I mean, clearly as we go to the right, this data looks like it's trending downwards. And you might say, well, that's, not that big a deal. But notice that this graph is the way all of our graphs should be when we can manage it. It has a true zero down there. We don't start at the lowest value of 48 degrees and go up to the highest value of 70 degrees. We show this with a true scale. Now, if you started at the lowest value and you only showed it to the highest value, you could make this look far more exaggerated. It would clearly be falling as it went to the right. We're showing that this is a significant but a modest effect. When you drive up into the mountains, it gets cooler, is the upshot. So now for a time series. So we're going to look at what happens over time. So a time series plot is a graph showing the data measurements in chronological, that is time order. The data being quantitative data, so that is like quantities, like numbers. For example, a time series plot is used to show the profits over the last 5 years. To create a time series plot, the time is always goes in the horizontal or the x-axis, and the other variable goes in the vertical axis, what would be the y-axis. Then plot the ordered pairs and connect the dots. So the purpose of a time series graph is to look for trends over time. So this is our last example. We're looking at some trends over time. I've been sitting a lot for the last few months, and so I look at this and it looks pretty darn good to me. As the months pass, it looks like this person's weight went from about 200 pounds to 190. And again, you may say, well, that's not all that significant, but hopefully they're healthy and happy as well. So we make a time series plot, and we see that, it's tending downwards. 10 pounds is 10 pounds. That's impressive, especially in these times. You might say, wouldn't it be kind of more interesting to show it like this? In other words, kind of a little bit above the maximum and a little bit below the minimum, and you can see, oh my golly gosh, we are making progress, if that's our goal, to lose some weight. Is that exaggerated? Well, it depends on your purpose. If this was me, I would probably make a graph that went from 800 to 205 just because it shows progress. There is definitely a trend there. And I'm kind of interested to see that. That looks good to me. So I probably wouldn't share that. I certainly wouldn't put it in a journal article or in anything that was shared with my colleagues because it doesn't have that true zero. I would use the graph that starts with 0 and goes all the way up. But for my own purposes, I probably would exaggerate it. Is it exaggerated? I don't know. I think if you have to look at the goal for these things. So there's chapter 2 that'll get us through our review of the book, and you'll get a PDF with instructions and some examples and some questions for the chapter 2 exam. It's essentially a take-home exam that you're going to do with R. So that's a whole other thing, and I will get that out to you as a PDF. So enjoy, and I'll see you soon. Bye.